And I would start, like all others, with thanking the organizers for organizing this nice workshop and also for giving me the opportunity to present here part of my work. The talk is based on joint work with Selina Drews from the Technical University Darmstadt. She is a PhD student of mine, and Adam Krishak from the Concordia University of Montreal. Okay. My presentation will be divided into 4 parts. After introduction, in the first part to the topic of the talk, I will introduce the kind of deep neural networks, overparametrized neural networks, which are learned by gradient descent, which I will consider in the rest of the talk. Then in the third part, I will consider the case, or I will show a result. Basically, such results are already known, and this is one of them. One of many results of these sets, that these estimates are able to minimize the empirical L2 risk if they are learned by gradient descent. So if you make this training long enough, and if you use sufficient small step size, and if the estimate is sufficiently overparameterized. And then I would like to argue that in the context of non-parametric regression with random design and an arbitrary design measure, such a property is not good for an estimate. That's the third part. And the fourth part, I will consider these kind of estimates in a setting where I do not train them so long. And in this setting, I'm able to show some results about the consistency of the estimates. So let me start with the first part, the introduction. It's well known to all of you that deep neural networks have achieved in the past, say, 10 years, impressive results in various applications, for instance, in image classification, text classification, machine translation, or mastering of games. And usually the successfully applied neural networks estimates in these applications are overparameterized. Overparameterized in the sense that they have much more parameters than data points. And the question, what I will look at it from in this talk, the question at which I will look at this talk is what are theoretical properties of such overparameterized deep neural networks estimates? Can I say something from the theoretical point of view that this is a good idea to use these kinds of estimates? Or why are these from a theoretical point of view good estimates? To do this, I will study neural network estimates in the context of non-parametric regression with random design. And here's the standard setting. It's a similar setting as we had yesterday in Claire's talk in the afternoon. You have an RD times R value random vector xy, a y square interval. You get an i.i.d sample of it. So you have random variables x1, y1 up to xn, yn given, and that's my data set dn, which consists of random variables which are independent and identically distributed as xy. And the goal is to construct an estimate, so a function from RD to R, which somehow uses, or somehow you want to use the data, dn, your data points, to construct such a function, such as a good approximation of the regression function. M of x, or m of small x, is the conditional expectation of capital Y given capital X is equal to small x. And this, if I want to make a connection to the talk yesterday afternoon, this regression function is the function which minimizes the mean squared error, empiric or L2 risk. And if you want to find an estimate such that its L2 risk is close to the optimal value, then it's equivalent that you want to have that the so-called L2 error, the integral of m of x minus m of x squared, integrated with respect to the distribution of x, is small. And that's what I'm aiming here in the SQLite. And due to the fact that in this L2 error, you use an integration with respect to the distribution of x, you can derive here results without assuming that x has a density with respect to the Lebesgue measure, or x could also be a discrete distribution. It won't hurt you. There exist quite a few results for least squares neural network estimates, and in these classical results, the estimates are not overparameterized. For instance, it's well known that these estimates can be universally consistent. So if you make a neural network, a class of neural network with one hidden layer, and you let with sample size n tending to infinity, the number of neurons tend to infinity, then these estimates turned out to be universal, and you compute in least squares estimates. So you use the neural network which minimize the empirical L2 risk, the empirical risk on your data points, and you don't bother how you compute it, so you don't use anything like gradient descent. Then these estimates are universally consistent in the sense that the expected L2 error of this estimates converge to 0 for all distribution of xy with expectation of y squares less than infinity. There's also, by nowadays, I think, classical result from Andrew Barham from 1993, 1994 concerning the rate of conversion of least squares neural network estimate with one hidden layer, and showing that they can achieve a dimension-free rate of conversion result in case that the Fourier transform of the regression function has a finite first moment. And then more recently, in the last 3-4 years, it was shown that deep neural network have some nice property, or least squares estimates based on deep neural networks have some nice property. They achieve a dimension reduction in case that the regression function satisfies a smooth hierarchical composition model, so that the regression function is a composition of functions, iterated composition of functions, which depend, where each of the function depends only on a small number of variables. And in this case, and if d star is the maximal number of variables on which one of these functions depends, then you get d star dimensional rate of conversion instead of the d-dimensional rate of conversion, where small d is the dimension of x. And the big question is, can you get similar results also for neural network estimates learned by gradient descent? In particular, in case that you are losing, or maybe to be useful here in this context, to use overparametrized neural networks. And what I will give you a positive answer to the first question about universal consistency today. I have positive answers to the second questions, but I'm not talking about this one. And I have no idea about the dimension reduction in case of a smooth hierarchical composition model for an estimate learned by gradient descent. That's an open problem. Okay, here's the estimate which I will, or the estimates which I will consider in the sequel. I use the standard logistic squasher. Sigma of u is 1 divided by 1 plus e with exponent minus u for simplicity. And I use a special topology of the network, and it's written here in a complicated way, but it's really something rather simple. What you are doing is you have capital Kn, many fully connected neural networks, which you are computed in parallel. Each of these fully connected neural networks has depth capital L and width small r. And then you see here the definition of this. So here you have the linear combination. And then these fully connected neural networks, which are computed in parallel, they have nothing to do to each other. So they use different weights. And they are recursively defined here. So the case of these networks just use the outputs of the other neurons in this case networks, and so on. And then on the level 1, you just make a linear combination of the input, and the input has dimension small d, and the input is x with upper index 1 to x with upper index d. Yeah? And then I have weights here. The numbering is not so important, but I explain it anyhow. So the first number, the k here, is gives you the number of the parallel network you are in, and then ij means you go from neuron j in the previous level to neuron I in the actual level, and L is the level here, and so the level L depends on, and in between, yes, as usually you apply the activation function, which is for me the logistic squasher. then you learn this by choosing the initial weights randomly. And I will later explain how you choose these initial weights. And then you minimize somehow modified empirical L2 risk, or it's first modified in two respects. First of all, later on, I want to get estimates which are consistent regardless whether the distribution of X is bounded or not. And in order to achieve this, I restrict this here to some cube minus alpha n this power d. And alpha n will tend to infinity later on, or maybe in some of the results in the third step, in the third section, just alpha n will be infinity. So you can, in this sense, you can ignore this indicator function here, but otherwise you just use the data points xi, yi, which are in this cube. And then I also use some regularization, and the regularization is a constant C2 times the sum of the squared of the weights of the output layer. Nothing else. And this C2 might be 0. That will happen in the third part. So then there will be no regularization at all. But also it might be, but in the fourth part, when I will present some positive result about consistency, it will be a number between 0 and infinity, finite constant.
Will that constant depend upon n?
No, this constant does not depend on n. It's just a constant. It's one fixed number. Thank you for the question. And in the third part, it will be even 0. Well, it's a very mild regularization. I could also use it for something going to 0, yeah, for n tending to infinity. And in that sense, I could use it to bound, or it would be helpful to bound the generalization of the networks, to bound some of the weights. But I don't do this here. It's actually, this comes only from my technique of analyzing the gradient descent. It's not need for the generalization of the estimate.
Understood.
Okay, and then we make a standard state gradient descent. So we start with W0, and I have a step size lambda n, and I define WT plus 1 as WT minus the step size. Step size is constant, but depending on n, and will converge to 0 for n tending to infinity, times the gradient of Fn, evaluated at rate Wt, and I do this for t equal 0 to Tn minus 1. So Tn is the number of gradient descent steps, and that will be later on the number which I will choose depending on n, and which tends to infinity for n. And then I need one more trick due to the fact that later on I want to get a universally consistent estimate. I have to truncate it. So I set the Mn of x is equal to some truncation of the neural network f with weight vector Wtn, where the truncation is made in such a way that, well, I use the original value if the value is between minus beta n or beta n, but if it's larger than beta n, then I just choose beta n. If it's less than minus beta n, then I choose just minus beta n. That's this truncation operator here, and I will choose beta n later on. In the third part, beta n will be just infinity, so there's no truncation at all. Alpha n will be infinity, nothing here.
You can think about that truncator as a final ramp sigmoid applied to the output.
Yeah, I cannot think about it.
But you're not plugging it into the least squares.
I'm not plugging it into the least squares because then
Easier this way.
I think I will have, oh, wow, okay. If I do it for least squares estimate, standard least squares, then I cannot compute the least squares anymore. At least in case of a linear least squares. I think it not a problem that if I make it here with the gradient descent, that's right. But I don't need to do it in this way. But you are right. Okay, and also I set the estimate equal to 0 outside of my showing interval. And I want to stress also due to overparametrization, it suffices to make one random initialization. I don't make repeated initialization and use the best one. Okay, then let me come to my third part. What can I say about where I will deal with estimate minimizing the empirical L2 risk? And first of all, I want to like to show you a result which shows, okay, basically you can, the gradient descent works in this setting under usually under some parameters in the sense that you find the global minimum even. Okay, what's the setting? I initialize the weight vector by setting all the output weights equal to 0. Choosing all the inner weights from some uniform distribution such that all the components are independent, and the uniform distribution is uniformly distributed on minus n to power 4, n to power 4, n is the sample size. Then I find the estimate as above, with C2 is in this case 0, so I need no regularization, and I need alpha and beta n equal to infinity, so you also need these truncation tricks, not at all. And then the first result is something from myself and Adam Krishak, which appeared, I think, this year or last year in Bernoulli. Well, assume R, that was the width of the neural network which you compute in parallel. That should be greater than equal to 2D, but could be arbitrarily large. Then L, that's the width of the network, should be at least 2. But 2 is possible, but you could also make it large. Then Kn is some large polynomial. Think about L equal 2, then this term here just vanishes, but then you still have a n with power 5 R times d plus 2 plus 7, and R is at least 2D, so R could be 2D, so that's a large polynomial you have. Then the step size is very small, 1 divided by very large polynomial, so L again could be equal to 2, but it still will be 1 over n with exponent 8 times R times d plus 1 plus 16L plus 15. And R is again at least 2D, so this is huge. Then Tn is extremely large in that way that basically lambda n times Tn is approximately n squared. So there's a relation between Tn and lambda n. So it's a little bit more than 1 over lambda n, maybe n squared more than lambda n. And then the claim of the theorem is, or the assertion, if n is sufficiently large, if you happen to be on the event that the different values of the xi, so not the same value could occur several times, but there where the data points take on different values, that should be separated in the sense that the subnorm distance is at least 1 with 1 divided by n plus 1 over 3. The maximum subnorm of the xi is bounded by 1. The maximum absolute value of the yi is bounded by n squared. Then you have with a high probability, the probability is 1 minus 1 divided by n, that the empirical L2 risk of your estimate learned by gradient descent is less equal than the optimal values plus some small term. It's 1 over n times log n. Well, and that shows it's great, yeah, because it shows if you think about gradient descent, yeah, you can say, okay, gradient descent, does it really find the optimum? Yeah, oh, something. It finds something close to the optimum in case that that your step size is very small and the number of gradient descents is very, very large, and the number of gradient descent steps is very, very large, and the number of parameters is huge. But is this useful at all? Well, here's a negative result. So I don't think that this is a useful result, and that lets me explain this next. Or that is the useful property of an estimate. I consider an estimate, it could be my neural network estimate from just before, but it could be an arbitrary estimate. So this is not about neural networks. This is a lower bound for a general estimate. This estimate depends on the data points and on some additional random parameter. This random parameter in the case of my neural network estimate is just a random initialization. And this initialization is independent of the data set. I have some kappa n greater than 0. Kappa n will later on be a small number. I have delta n, that's my distance of the x values, should be less than 1 divided by 1 divided by n plus 1 with power 3. And assume that the estimate satisfies its empirical L2 risk is less equal than the minimum possible value plus this kappa n. And this kappa n in the previous slide, that was just 1 divided by n times log. No, it was, yeah, it was here. It's 1 divided by n log n, yeah? You can think of kappa n as 1 divided by n log n. Then Okay, and this should be true whenever the subnorm distance of the xi's, also of these x values, have some subnorm are separated by the delta n. Delta n could be 1 over n plus 3, n plus 1 with power 3, and whenever u is in Pn. And then the claim is there exists a distribution of xy such that x is in the unicube, the supreme. Oh no, sorry. There exists a distribution of xy such that x is in the unichrome, y is in -1, 1, almost surely. The regression function is constant 0, and such that you have for n greater or equal to 10, the expected L2 error of your estimate is greater or equal to 110 minus n times kappa n minus 1/2 times the probability that u is not in Pn. Okay, what does this imply? Here's a corollary.
A question.
Okay, sure.
Does this hold for every m or some m? This theorem?
No, this holds for every estimate, Mn, but it exists a distribution with all these properties here. So the m is fixed.
So the conclusion happens for one m.
The conclusion is this is an existence theorem. There exists a distribution where this regression function m is constant 0, and your expected
like m is very irregular, then that's not very surprising, no? I mean, you just
zero.
No. M is very smooth.
So m is 0 in the okay, I see. Okay, I get it. No, I overlooked that. Thank you.
Michael, I'm a little confused because you have no conditions on the size of the network.
This has nothing to do with network. You don't need a network. This is not about a neural network. This is about an arbitrary estimate. As soon as an arbitrary estimate has this property that its empirical L2 is small, there exists a bad distribution. That's my claim.
Oh, you're overfitting.
I'm overfitting, yeah.
Oh, so it's a theorem about overfitting. If G
it's a theorem about overfitting.
If G gets too close to a noisy Y, it will be bad.
Yeah.
Gotcha.
And the point will be that, or the distribution actually will be discrete. So you have so the xi's are so the x is a discrete distribution, and then you have these y's which are -1 and 1, yeah. But in the counter example, they have nothing to do with x, and they are -1 and 1 each with probability 1/2, yeah. And then if your x1 up to xn are somehow distinct, then you interpolate all these yi's, and that's bad, yeah. Because
you did not restrict the g's at all. So this gets close to the minimum over all functions.
Yeah, it's the minimum over all functions. Yeah.
All measurable or whatever.
Yeah.
Because minimum over G is 0, no?
Excuse me?
The G's, yeah. Okay.
The minimum over G is not 0 because the xi could be, you could several times have the same xi.
Right. But if the x's are distinct.
If the x is distinct, then the minimum is 0.
That's going to be 0.
If not, then you might then you will get a minimum just by using this function, which has the g of xi is the average of all those yi's where xi is equal to this, or g of x is the average of all yi's where xi is equal to this x.
That's clear. So any kind of meaningful statement involving such a minimum usually would concern a restricted class of g's, no? I mean, like this class of g's is just so large that it's clear that no estimator can satisfy it.
Yeah, but that's what you have for this estimates, or that's what you have in case of the interpolation. If you come up with a neural network which interpolates your data, yeah.
Now we understand. Aha. So here too, in your minimizing empirical risk, that wasn't over neural nets G. That was again essentially 0. So you're saying that with such a huge network, you can get essentially 0 error.
Well, parametric rate, because you have the 1 over n log n. Right. So you're just saying you get the 1 over square root n rate basically in the empirical risk, no? Because the leading term here is just 0.
Oh no, I don't get it. So well, oh yeah, right. If the xi's are all distinct, really, then I get 1 over n log n.
Right, what do you think you want?
But you
You can make it anything you want.
But that, I mean, okay. So
okay, but maybe I go on. Maybe then it will be clearer because there's one more theorem, and or one more corollary, which maybe makes put it in the right setting. Yeah. So let M be either the estimate of theorem 1, or let it be in. Or this estimate of theorem 1 has the following property. It satisfies the assumption of theorem 2 for kappa n is equal to 1 divided by n log n, and some set Pn, which has the probability that u is not in Pn, is less equal than 1 over n. Let PC C1 be greater 0. Let dPC be the class of all distribution of xy where x is in the unit cube. The conditional expectation of y square given capital X equal small x is bounded by C1, and M, the regression function, is PC smooth. PC smooth means something like if P is not a number, it's P times continuous differentiable. Then you have for n sufficiently large the subnorm error of your, or the minimax error of your estimate over this class dPEC is greater equal 1 divided by 11. It does not converge to 0. And that's bad because it's well known for this class dPC. You can find estimates, for instance, standard kernel estimates or least square estimates with splines, where this subnorm error is bounded by some constant times n with power minus 2p over 2p plus d. So these estimates do not achieve the optimal minimax rate of conversion. And in this sense, I would say they are bad.
So Michael, this fact that these estimators would be bad is natural for a statistical audience, but it's still something that needs to be heard because the going thing in neural nets is to use a hugely overparameterized network that has the potential to achieve this nearly zero empirical error, and they still say it's going to be great. And so this is a reminder of what, as mathematical statisticians, we would think to be true, that no, they're going to be bad.
Yeah, okay, let me defend the machine learning community here. So everybody knows that if you take any interpolating estimator, it may be very bad. But the one that you achieve by the descent is special. It does minimize a certain norm. Maybe this is where Michael is going to get too soon, but it's not any minimizer. So if you take a random interpolator, it won't work. But the one by the descent does work in practice, and there are theory to
agree.
Okay, but maybe let me mention it's bad in the sense that you allow arbitrary distribution of x. Of course, the story is different if you restrict the distribution of x. For instance, in Claire's talk, we had x was a uniform distribution. As soon as you assume that x is a uniform distribution of on some compact interval, then this lower bound does no longer apply because it requires a discrete distribution. Also, I should stress that here the worst distribution changes with the sample size.
Yeah, your bound is bad. It does not mean the method is bad.
Excuse me?
Your bound is bad because it relies on the empirical risk. It does not mean the method is bad.
No, I just want to say that this bound or this existence theorem does no longer apply if you restrict yourself to distributions which are uniform distributions, or if you have a density with respect to the Lebesgue-Borel measure bounded away from 0 and infinity on some interval, then it does no longer apply. Okay, that's my point here. Okay, but next is something positive about overparameterized neural networks. I want to show something. You can still achieve some good results from a theoretical point of view with overparameterized deep neural networks in case that you do not chain so long that your empirical L2 risk basically becomes minimal. And here's the setting. I choose again the outer weights all to be 0 and choose all other weights randomly such that the components are independent and such that all weights on the levels 1 to small or L between 1 and capital L, they are uniformly distributed on some interval of some logarithmic lengths. So minus 20d times log n square up to 20d times log n square. And all weights of level 0, they are uniformly distributed on an interval minus n with power tau, n with power tau, where tau is between 0 and 1 divided by d. Then I define the estimate as above. This time, this constant in front of the regularization term is fixed and greater 0. So I use the regularization, and I also use this truncation. You will see on the next slide, the alpha and beta n will be some log factor. Then I can show the following theory. Assume again, this tau is between 0 and 1 divided by d. Assume R, this was the width of the neural network which you compute in parallel, is at least 2D, could be 2D. L is at least 2. 2 is sufficient, but it could be arbitrarily large. Kn goes to infinity slower than some polynomial. So Kn divided by n over n with power exponent kappa goes to 0 for n tending to infinity for some large kappa greater 0. And Kn goes quicker to infinity than n with power r times log n. So observe R is at least 2D, so Kn will be larger than n with power 2D. So indeed, you have an overparametricized neural network. You choose alpha and beta n equal to some log factors. I choose the step size as 1 divided by ln. Ln is defined below. The number of gradient descents is constant times ln times log n. So basically, the step size times the number of gradient descent step this time is not longer n squared, but it's log n. It's a logarithmic factor. And ln is large because Kn was large and ln is larger than Kn with exponent 3 divided by 2 times some log factor. You define the estimate Mn as above. Then you can show that the expected L2 error of your estimate converges to 0 for every distribution of xy with expectation of y square less than infinity.
Michael,
Yes?
there's an aspect of this that puts it outside of the range that people would like. So you need k, your number of final layer neurons, to be a smaller order than n to the 1 over d. And typically, I mean, okay, you can use that for d small to say something interesting about a big network. But if in typical applications, d is really large, typically larger than sample size.
Yes.
Then n to the 1 over d is just barely bigger than 1. You know, so you're not really allowing a large number of neurons. In fact, the two conditions become inconsistent. Because,
no. There is a tau and there's a kappa.
Yeah.
I
thought that the tau was, it's a visual problem.
I'm sorry, I made this mistake myself sometimes when I'm reading this article. So the tau controls this initialization of the inner weights.
Oh.
This one. That
okay,
will be
fine.
But
so they happen to go
is,
from -1 to 1. Okay.
But
Gotcha.
the kappa is large, yeah?
Yes.
So another question, is this result now uniform in a reasonable class of M's, like a Lipschitz ball or something?
Yes, it's uniform in the Lipschitz class, but I don't get it. Well, actually, in order to get a positive result for the previous section, I should formulate it as a minimax bound, yeah? And it's a minimax, but it's not the optimal rate. I don't get the optimal rate at the moment. So therefore, we just have proven uniform consistency. But I get for Lipschitz continuous regression function and bounded x, and maybe bounded y, but I can weaken the condition bounded y. I get a rate of conversion uniform over this class.
I have a naive question.
Okay.
Here you initialize to 0 the output weights and you take random input like inner weights. But do you need to optimize the inner weights? Could you simply optimize?
Let me say you something about the proof. Okay? If you don't mind, and because it's the next slide, I make some remarks. Yeah. The first remark is I control the complexity of the network by bounding the initial weights. That's this condition 0 less than tau less than 1 over d for the weights on level 0, and by logarithmic bounds for all inner weights, and by bounding Tn times lambda n by some logarithmic term. this last condition enables me to show that during the gradient descent, all weights change at most by some logarithmic term. So that the weight at times Tn minus the weight at times 0, the corresponding weights, the absolute value is bounded by some constant times basically square root of Tn times lambda n I can show. And then I know for the last step 2 times Tn, I know I have some nice bounds on all the weights. I have bounds on the output weights because they are original 0. So at the end they are at most kn. All at the end they change at most by some logarithmic terms. So I know all of them are bounded by some logarithmic term. All the terms between level 1 and L are bounded by some logarithmic terms, and the inner weights, they are bounded by n with power tau. And then I can use some metric entropy bound based on this classical metric entropy bound, for example, the result of Biermann and Solomyak. So you can compute the partial derivative of your neural network. It's easy to see. Excuse me, is there a question?
Yeah, so essentially your inner weights are not moving. So what we're doing is proving a result about random features learned by gradient descent in a convex with a convex loss, which is.
Oh, the inner weights are moving.
Yeah, but by a tiny bit, and I almost that you get the exact same result by keeping them fixed and only optimizing the last layer, which is a convex problem for which everything is known.
Well, I agree. I can do the same real theory much easier if I just make the gradient descent just on the last layer. That's right.
The same result is not better.
No, but it is not about this is not about that I can prove that some estimate is universally consistent. You know, since 1977 that there exist many universally consistent estimates. The surprising fact is that the overparametrized deep neural network has this fact learned by some gradient descent.
Sure, but if you just fix all the weights except the last layer, you still overparameterize and you're still doing gradient descent. So
you can still do the gradient descent and you can still prove this result, but that's not the point here, because the result is not especially what I want to say. I have many estimates which have these properties. I don't need a neural network for that. The surprising result fact is that if you learn a neural network by gradient descent, you can get such a result. That's the point here, which I would like to make. But maybe let me finish my talk and then we can discuss more. Okay, that was the first remark. So I learned this trick without using a metric entropy bound by some recent paper by some Chinese guys, which I found by accident. And this is very useful here. The second thing, due to the regularization, I'm able to show that the gradient descent is choosing the outer weights in an optimal way. And you are right. And actually, what I use is that I minimize only or that I optimize only the outer weights, and the inner weights don't change much. And then I use the overparametrization implies that a subset of the Kn fully constructed neural network is able to represent a piecewise constant approximation of the regression function in such a way that even if you change this inner weights a little bit by this log factor, it doesn't change at all. And that's enabled me to prove the results. Okay, let me summarize my talk. First point, the overparameterized neural network estimates learned by gradient descent are able to interpolate the trainer data. My claim is that such estimates do not generalize well because they are not adapted to arbitrary design distribution. But if you restrict for such estimates the number of gradient descent steps and the step size properly, then this leads to overparameterized neural network risk estimates which are universally consistent. Thank you for your attention, and I'm happy to answer any question.